Hello, welcome to lecture 11 of our analysis course. Today we're going to talk about Cauchy sequences. We'll start with a quick review. Last time we were talking about monotone sequences. Monotone sequences are those that are either increasing or decreasing. And we showed a theorem that if a sequence is monotone and bounded, then it converges. This is a very important theorem because it gives us a criteria to know that some sequences always converge, even if we do not know the limit. So our goal here is to obtain certain tools to be able to show that a sequence converges. Rigorously, even if we do not know the limit of the sequence in advance. This result is the first result of this form. So this is one criteria. If your sequence is increasing or decreasing and bounded, then it converges. And we're going to see another criteria to be able to do this in another way. Lim sup and lim are important tools to be able to do this. And Cauchy sequences, which we will define later today, it's going to be the general concept that allows us to do this. So, from this result that bounded monotone sequences converge, we also obtained the following fact, that if we only know that your sequence is monotone, say increasing or decreasing, let's say it's increasing, always increasing, then its limit always makes sense. That is, if we call this limit L, then L is either a real number or plus infinity. So in this case, it diverges. This is the case where it is not bounded. So it diverges, but it diverges to plus infinity, so the limit still exists. So this still makes sense. And the same thing with decreasing functions. If it is decreasing, the limit always makes sense, and it's either a real number or minus infinity. So now, let's make a quick review of lim sup and lim inf. Let's go back to the previous lecture. And we have some nice pictures here. So we're going to take our sequence, and we're going to consider only the elements that are very large. So that the n, the index here, is very large, larger than some cutoff n. In this picture, we can see a certain sequence that's oscillating a little bit, and we are taking a certain cutoff. And from this cutoff forward, we're going to take the sup of the sequence. So from this point forward, the sup is this purple line here. And we're also going to take the inf, which is the lower bound. So from this point forward, the inf is this point here, this purple line here. And if you take your n, your cutoff points, to be bigger and bigger, then the purple lines get closer and closer to each other. The infimum gets a little bit closer to the supreme. They don't necessarily coincide, but the upper bounds become smaller and the lower bounds become bigger. This means that these are monotone sequences. And since these are monotone sequences, then they have a limit, their limit exists, they converges, and that limit is what we call the lim inf and the lim sup. So the lim sup here, this is the definition from this class, the lim sup is the limit of the sups from this cutoff, the limit where the cutoff goes to infinity. And the lim inf is the limit of the inf when the cutoff goes to infinity. So they always exist. Even if your sequence does not have a limit, this always exists because this is monotone. And if Sn is not bounded above, the limit sup is infinity. If it's not bounded below, the limit is minus infinity. So this is the concept that we defined. Let's make another picture here. Let's say this is R2, this is a graph, this is the point 2. Let's make it a bit. Let me try this again. Say here we have the point 2 up here, the point 1, the point -1, and -2. Let's draw a line here, here. Let's consider some function that does something like this. Something like this. And let's say that your sequence lies along this function, something like this. So let's say that these black dots are your sequence. So this here is your A1, A2, A3, A4, A5, and so on. Let's not worry about any precise definition, let's just look at the picture. And what I'm trying to say here, this is going to be oscillating a lot, but it's going to be getting, these points here are going to be getting closer asymptotically to this pink line here, and these points here are going to be getting asymptotically closer to the pink line here. So that's here the sup of the sequence. The biggest element of them all is going to be, let's say we have this one a little bit here above. So we can say that this is going to be the sup. This is the highest of all the points, and the infimum, the lowest one, let's say that we have this point maybe a little bit here below. So this is going to be the inf. A2. Everyone else is going to be between this and this. Now if we take some larger cutoffs, let's say from 3 onward, this is going to be the sup from this point forward, even though it's a little bit below. Let me extend this line, something like this. Like this. So let's imagine that this black is above the purple and this black here is below the purple. So from this point on, this is going to be the sup from this point forward, and this is going to be the in from this point forward. And if we keep doing this, since this is getting closer and closer to the pink line, then this pink line here is going to be the smallest of the soups. So this pink here, this is the lim soup. And this pink here is going to be the largest of the inf. This is going to be the lim inf. So the lim soup is smaller than the soup. The lim soup is something close to 2. The lim inf is something, the inf is something around here. But the lim inf is -1, and the lim soup is 1. Even though the sequence does not have a limit. So the limit does not exist, but the lim soup is going to be here, and the lim inf is going to be here. Okay, so now what happens if the lim soup is very close to the lim inf? This means that all of the points have to be getting very, very close to each other. When n is very large, they have to live within this space. So the theorem that we stated last time is theorem 10.7. It says that if your limit exists, either as a real number or plus or minus infinity, then the lim soup and the lim inf have to be equal to the limit. And conversely, even if you don't know anything about the limit, but if you know that the lim inf is equal to the lim soup, then the limit also has to exist, and the limit also has to be equal to both of them. So this is like a sandwich, like a squeeze theorem. We are squeezing the limit between the lim inf and the lim soup. And we're going to start by proving these facts today. So let me copy this. So let's read this again. Let Sn be a sequence of real numbers. If the limit exists, either as a real number plus minus infinity, then the lim inf is equal to the lim and to the lim soup. And 2, if lim inf is equal to the lim soup, then the limit exists, and again the lim inf is equal to the lim soup. So note here the important fact. The most important part is this points to. This gives the criteria. If you know something that has nothing to do with the limit itself, then you can show that the limit exists. Even if you don't know what it is exactly, you don't need to know what the lim inf and the lim soup are. You just need to know that they are equal. And if they are equal, then the limit also exists and it's equal to them. So this is an example of our goal here. To have a tool to show that a sequence converges without knowing the limit. This is why this is important, and this is why we care about lim inf and lim soup. That's why they are important concepts. We're going to write a rigorous proof today. So we have two cases here. And let's do part 1 first. So we're trying to show this. So we know that the limit exists, and we want to show something. We have 2 cases, because we have to, or 3 cases, we have to see what happens if the limit is plus or minus infinity, which is a different case, or if the limit is a real number. since those are different definitions. So let's do first the case where the limit is equal to plus infinity. And we have to show that both lim infinitum are also plus infinity. From the definition. Alright, so let's use the same notation that we were using previously for this. So let's call Ln, L for lower bound, Ln is equal to the infimum of our cutoff of the sequence. Sn for n bigger than big N. So the big N here is this big N here. And Un is going to be the sup of n larger than big N. U for upper bound. Okay, so now we are in this case. The limit is plus infinity. So what's the definition of this limit? Since by definition, let m be a positive real number, then there is a positive integer n such that for little n larger than big N, this implies that Sn is bigger than m. And this implies if all of your elements of your set are bigger than m, if you consider only these elements that are bigger than this specific n, all of the elements are bigger than m, this means that the infimum is also greater than or equal to m. Because the infimum is the smallest lower bound, and this is a lower bound, so this means that the infimum has to be less than or equal to them. Therefore, Ln is greater than or equal to m. Since this is the biggest lower bound. So m has to be smaller. Therefore, if m is bigger than big N, this implies m bigger than big N implies Lm bigger than big M. But this is exactly the definition of infinite limit for this sequence Lm. The sequence Lm M satisfies the condition defining limit of Lm equal plus infinity. But, so this is the limit of the infimums. We said that the limit of the Lm's, the limit of the infimum, this is our Ln. That's the limit by definition. So this exactly means that the lim inf by definition of your sequence Sn equals plus infinity. Since lim inf by definition is the limit of this Ln. So if we go here to this definition, this here is your L. So this shows that if your sequence converges to infinity, then the lim inf is also plus infinity. And it's similarly for the sup. Similarly, lim sup of Fn is plus infinity. So the other case, where the limit is equal to minus infinity, it's similar, it's doing the same, just flipping the signs. Flipping the inequalities for bigger than n, instead it will be less than minus m. Otherwise it's the same. So now let's do the general case where your limit is a real number. Your limit is equal to L, which is a real number. So neither plus or minus infinity. So the idea, what we're trying to say here, if this limit is equal to L, this means that Sn is very close to L for all large n bigger than something. And if this is very close to L for all large n bigger than something, this means that the supremum of all of the large elements is also going to be very close to L. And this means, by definition, that the lim sup of your sequence should be L. This is the rough idea. And what we're going to do is to formalize this with epsilons and so on. So here's the actual proof. As always, we start by saying that epsilon be greater than 0. Then, by definition of this limit, there exists natural number n such that Sn minus your limit is less than epsilon in absolute value for n bigger than big N. What does this mean? Remember that the absolute value here means two things. Equivalently, L minus epsilon less than Sn less than L plus epsilon. for n larger than big N. Here we are going to care especially about this inequality first. So if this is true for all n bigger than big N, then if we consider the upper bounds, un being the sup of dsn for n larger than n, all of the elements are less than L plus epsilon. This means that this is an upper bound for this set. If this is an upper bound for this set, this is the least, the supremum is the least upper bound. This means that the supremum has to be less or equal to this. So this is less than or equal to L plus epsilon, since the sup is the least upper bound. And the same thing holds if we take any element, any index here that's bigger than m, and bigger than big N, implies if we are bigger than big N, this means that we are still in the situation where this happens. If we take any m, I extend this n by an m. So this means that if we take the supremum of all of the elements larger than m, this is still going to be true. So this implies that um less than or equal to L plus epsilon. And this is true for all m bigger than big N. So now we can take the limit. That was one of the exercises. If your sequence is always less than or equal to a number, then the limit of your sequence is also less than or equal to this number. But the limit of this sequence, this is exactly by definition the lim sup of Sn. This is the limit of the sups. So this is lim sup of Sn is less than or equal to L plus epsilon. So what did we just say? We took any epsilon greater than 0, and for any epsilon greater than 0, we showed that the lim sup of their sequence is less than or equal to L plus epsilon. This is a number. This number is less than L plus epsilon for any epsilon. Since this is true for any epsilon, by another of our exercises, so it's an exercise in list 2, I think, and so is this. So is what I'm about to say. Since this is true for any epsilon greater than 0, then this has to be actually less than or equal to L. Now a similar argument. I leave the details for you to check at homework. L is going to be less than or equal to the lim inf of Sn. But we always have that the lim inf is less than or equal to the lim sup, because one is always defined as in terms of the infimums. The infimums are always less than the sups, so the limit of the infimums is less than the limit of the sups. Then we get this chain of inequalities. L is less than or equal to the lim inf, which is less than or equal to the lim sup, which is less than or equal to L. In other words, this is less than L and also bigger than L, so everything has to be L. Therefore, lim inf is equal to lim sup, which is equal to L, and by definition, or L is just the limit of the sequence, so everything is equal, and this is exactly what we were trying to show. So we showed that if your sequence converges, then the lim inf and the lim sup are both equal to this limit. Here, we are using this general idea of giving ourselves an epsilon of room. So we're playing with these epsilons here to be able to show that this lim sup is less than or equal to the limit. We actually show that it's less than or equal to the limit plus epsilon for any epsilon. And we can do that by using our definition of limit. This is what allows us to do this from this inequality here. So this is an upper bound, therefore the least upper bound is also less than or equal to that. And we can take the limits to obtain this inequality. And we can remove the epsilon, since this is true for any epsilon. And we can do the same for the lim inf in the other direction. So that gives us a chain of inequalities and tells us that everything has to be the same. And this is how it goes. So this concludes the proof of part 1. Which is this. So if the limit exists, everything is equal. Now we want to show the opposite, that we don't know anything about the limit, but we know that the lim inf and the lim sup are equal, then the limit has to exist and also be equal. So part 2. Assume that the lim inf is equal to the lim sup, and we must show that the limit exists and is also equal. To lim is equal to lim sup. Again, we have several cases depending on whether it's plus or minus infinity. And these are going to leave to you as an exercise. If lim inf and lim sup are equal to plus infinity, it's easy, it's relatively easy to show that the limit of Sn is also equal to plus infinity, just from the definition. Use especially this one. The infimum is small, so if the limit infimum is infinity, it has to be because everything is infinity, and then you can show this from the definition. You have to show that your sequence is not bounded. Okay. And similarly, if lim-inf and lim-sup are minus infinity, then it's not hard to see that the lim of your sequence also has to be minus infinity. You can show this from the definition as an exercise. So I'm going to do the other case. Actually work on this. This might show up in a future assignment. Okay, so the other case. Suppose that they are equal to some real number. Let's call it L. And it's a finite real number. And we have to show that the limit of Sn is also equal to L. So as always, if you take a look at the previous proof, we can see that there were more or less two stages. The first stage was using the sup, the lim-sup. We showed that the lim-sup was less than or equal to L plus epsilon. And on the other hand, the lim-inf satisfies this opposite inequality. So again, we are going to use two stages, one where we use the sup, one where we use the inf. We're going to use the lim-sup. So because we have two assumptions here, one is that the lim-sup is L, and the other is that the lim-inf is L. We're going to use the two assumptions separately for different things. It's basically, this is the same thing as saying A is equal to B means that A is less than or equal to B, and B is less than or equal to A. This general idea of how we can show that two things are equal is by showing these two inequalities. And the idea of giving us an epsilon of room, this is general strategy. Give an epsilon of room, useful to solve many problems, to prove many theorems. In this case, if you want to show that two things are equal, this is equality. Then you can also show, instead of showing these two inequalities, you can show that A is less than or equal to B plus epsilon, and B minus epsilon is less than or equal to A. For any epsilon greater than 0. This can be a little bit easier to prove than without the epsilon, because we have a little bit more space to show an inequality. That's what I mean by give yourself an epsilon of room. And again, this can also be a little bit easier to show than the inequality without the epsilon, because this is going to be a little bit smaller, so maybe since this is smaller, it's easier to show that this is smaller than A. And if you show these two things for any epsilon, this is, here I'm talking about strategy. If you show that these two things are true for any epsilon, or exercise from our list 2, these two things combined, this was from one of our exercises. This implies that we can remove the epsilon, and these two things together imply that A is equal to B. This is how I can explain this strategy in general. If you want to show that two things are equal, then you show these two things with an epsilon. And this implies that the two things are equal. So in this case, this is my A, this is my B. I want to show that this A is equal to this B, that the limit is equal to L. So I'm going to basically show that, roughly the idea, I'm going to show that this is less than or equal to L plus epsilon, and also greater than L minus epsilon. So there are two parts, this and this. For the first part, this is general strategy, but in our specific case, I have here two pieces of information. One about the lim sup and one about the lim inf. So I'm going to use this piece of information about the lim sup for the first part here. This is useful because the lim sup is talking about sups, it's talking about upper bounds. This is exactly an upper bound. That's why this part is useful here. And here I'm going to use the information about the lim inf for this second part here, because this is talking about a lower bound for A. That here we're talking about infimums. Infimums are lower bounds, and that's why this information here about infimums is going to be useful for this. So this is the general strategy. This general strategy that's very good for you to know for many sorts of theorems, for proofs, and for exercises. You're going to see it a lot through your mathematical life, maybe, if you do more things related to analysis. Now let's go to the proof. So as I said, first we're going to do this, and for this we're going to use the sup. So always let epsilon be greater than 0. Then we considered un to be the sup of the set of Sn for n bigger than big N, and we are assuming that the lim sup is equal to L. So we have that the limit of un is equal to L. This is by definition the lim sup. So just to make sure that we're clear on this, if I go back to the definition, this here is our un. So the limit of un is by definition the lim sup. So the lim sup is equal to L. Then what we have is that this limit is equal to L. And this means, by definition of limit, then there is an integer and 0 such that L minus un, but your un is just the supremum, so let me write the supremum, L minus the sup is less than epsilon. And again, this here is just my un. So this is just my definition of limit for this specific limit and for this specific un. And again, we can write it with absolute value, but equivalently. L minus epsilon less than the supremum, less than or un. And less than L plus epsilon. As always, an inequality with absolute value is equivalent to these two inequalities. And this is again my un. And as I said, here I'm working with the sup, and for the sup I care more about this inequality here, because here I'm talking about upper bound, so I care more about the upper bound. So in particular, if your supremum is smaller than this, this means that all of your elements are also smaller than this, because the supremum is an upper bound. So Sn is always less than or equal to the supremum, by definition of supremum. Which is less than L plus epsilon for n larger than big N. Big N this here, I'm using N0 here, so I should use N0 here, N0 here, N0 here, N0, N0. So I have one inequality here, Sn less than this. This is essentially what I have here. I'm not doing it with a limit, but I'm doing it with Sn. I'm saying that Sn is less than L plus epsilon, which is essentially what I wanted to say here. So let's summarize. Sn is less than L plus epsilon for n bigger than n0. So, okay, I obtained my first part. I obtained that my, not the limit, but my Sn is less than L plus epsilon. Now I'm going to do the second part. And for the second part, I'm going to do the same, but instead of the sup, I'm going to use the inf. So similarly, let's do the same argument. Since Ln, which is the infimum of Sn and bigger than big N, this converges to L. Then, by definition of limit for this sequence here, there is an N1 such that L minus the infimum of N larger than N1 is less than epsilon. And therefore, again, we transform this inequality in absolute value into two inequalities. I only care about the first one, so L minus epsilon is less than the infimum and bigger than N1. And this is also less than L plus epsilon, but I don't care about this one. I only care about this one in this case, because I am following this strategy here. This is more or less what we're seeing. But I don't want this with the infimum, I want this with the sequence. Notes that, so this was my general strategy, but I cannot actually do this with the limit because we do not yet know that the limit exists. That's why this is the general strategy, but we have to adapt it a little bit for our situation. In our situation, we're going to do this with our sequence. So this A is going to be like your sequence as n for large n, and this B is going to be your limit. So Sn less than L plus epsilon and L minus epsilon less than Sn. And okay, so we have this bound here. If your infimum is bigger than something, that means that all of your elements are also bigger than this something because the infimum is a lower bound. So we have Sn is greater than or equal to the infimum by definition of infimum. For n bigger than 1. And we just said that this is bigger than L minus epsilon. So we have this inequalities here. This means that L minus epsilon is less than Sn for n bigger than n1. This is exactly what we wanted here. And again, this is basically the strategy that we were following. This is what we wanted. So now, we're actually going to apply the definition of limit to show that the limit of Sn is equal to L. We already have an epsilon. So now let big N equal to the max. This is always what you have to do when you have two different n's, is to take the maximum. So the maximum of n0, 1, and 1. Then n bigger than big N implies if it's bigger than the maximum, then it's bigger than this one, and it means that this is true. And it's also bigger than this one, so it means that this is true. So we have the two things. So we have L minus epsilon less than Sn less than L plus epsilon. Or equivalently, Sn minus L is less than epsilon. And this is the definition of limit. This is true for any epsilon greater than 0. We started by letting epsilon greater than 0. And we show that for any epsilon there is an n, such that n bigger than big N implies this. And this is exactly what the definition of limit. Equal to L as we wanted. And this finishes the proof. And I want to highlight again that this is the general strategy that we're following. To show that A is equal to B, you show two inequalities. And in this case, A is going to be, we're not doing exactly this. We're doing this where A is more or less your Sn for large values of n, and B is your limit L. So we're showing that Sn is less than L plus epsilon, and also that Sn is this other inequality for large n, and that's basically the definition of limit, combining those two things. But this general strategy can be adapted in many different ways for different problems, different proofs, different theorems, so it's good to know that this is the general idea that we are following. And right, this is the proof. So now we have a tool to be able to show that a limit exists even if we do not know what the limit is. But if we can check that these two things are equal, then the limit exists and it's also equal to that. So again, if we go to the beginning of what we said to start, Our goal is to show that a sequence converges without knowing the limit. We already gave a tool for that. But now I'm going to give you a definition of Cauchy sequence. And I want to say that because this is a very general, this is that way of showing that a sequence converges without knowing the limit. We were going to use our tools of LinSoup and LinMinf, but basically I'm going to tell you what a Cauchy sequence is, and I'm going to tell you that Cauchy sequences are always convergent. So if you know that a sequence is Cauchy, you also know that it converges. The idea is the following. So if Sn converges to a certain limit, this means that Sn is very close to L for large n. Let's say instead of saying for large, let's say for large n bigger than something. And this means, let me just change the m. Let me take another different m that's also bigger. So Sm is very close to L for large m bigger than the same something. But so if you take two different indices, n and m, and they both are large, then both of these things have to be very, very close to L. And if this is very close to L and this is very close to L, then this has to be very close to this. Sn has to be very close to Sm. For large n and m both bigger than n. So as long as your indices are large, you can take any two indices as long as they're both large, and your elements are going to be very, very close to each other. And what's interesting here is that I'm saying something here without saying anything about the limit. I'm just saying that the elements are close to each other when the indices are large. Whenever this happens, that's what we call a Cauchy sequence. So a Cauchy sequence is a sequence where your elements are very close to each other whenever you take large indices. So as we said here, if your sequence converges, then it is also Cauchy. Your elements are close to each other. Let's write down the official definition, the formal definition. This is definition 10.8 in the textbook. So a sequence Sn of real numbers is called a Cauchy sequence. If, and now I'm going to say exactly this, but I'm going to say it in more precise mathematical language of epsilons. That's the language we've been using throughout the course. So now let's see if we can formalize this in terms of epsilon. I'm saying that this is close to this. How do we formalize saying that something is close to something? A is close to B if A minus B is less than epsilon. That's how we say this more formally. In absolute value. The absolute value is always talking about the distance between A and B. So this is more or less how we say this. So we are saying that Sn is close to Sm for large indices. So the difference between this and this in absolute value is less than epsilon when your indexes are large. So for any epsilon greater than 0, there is natural number n such that both m and n bigger than big N. So now we have two conditions. That's what I was saying here. Implies absolute value of Sn minus Sm less than epsilon. This is what I was saying here more intuitively. This is how we formalize this mathematically in terms of epsilons. So I'm basically saying that Sn and Sm are very, very close to each other because their difference is less than epsilon. Okay. You should compare this definition with the definition of limit. So, as we said before, this is intuitively the definition of limit, that your sequence is very, very close to L when your index is large, and the way you formalize this is by saying that for any epsilon there is an n, such that when your index is large, Sn minus L is less than epsilon. So this is a similar definition, but now without any limits, just the sequence. And a Cauchy sequence is a sequence that satisfies this. Okay? So, first, maybe let's copy the definition so we can keep it in hand. So our goal here is to show a theorem that says that Cauchy sequences converge. Cauchy sequences are exactly convergent sequences. So you can always check that a sequence converges by checking that it is a Cauchy sequence. That's our goal. We're going to show this in this class. For now, we're just going to say a few lemmas. This is our definition, and now let's say lemma 10.9. One direction of this is relatively easy. Is saying that if your sequence converges, then it is also Cauchy. That's relatively easy to say. Convergent sequences are Cauchy sequences. The idea of the proof is essentially what I was saying here. If this is close to L and this is close to L, then this is close to this. How do we formalize this? Anytime that we have two things that are close to something, and the way to show that they are close to each other is by using the triangle inequality. That's all that we're going to do. You have seen this argument several times, so I'm just going to write it. Suppose L is the limit of your sequence. We're assuming that it converges. We're assuming that its limit exists. Let epsilon be greater than 0 by definition of limits. There is n such that n bigger than big N implies Sn minus L is less than epsilon divided by 2. Why divided by 2? because we are going to use two pieces of information. This one and this one. In fact, if you don't do the equal epsilon over 2, what's going to happen is that at the end you're going to get less than 2 epsilon, and that's your sign to know that you had to use epsilon over 2. We cannot read the future and know this in advance. You just work it out in your scratch work, and then you realize that you have to divide by 2 here. Now I'm going to write this same thing. I'm going to change the n by another m. We can also write m bigger than n implies Sm minus L less than epsilon over 2. This is the same thing. I'm just changing the symbol. Therefore, if you have two different variables, m and n bigger than big N, this implies that two things happen. So, now let's say what we want to obtain as n minus m. I'm going to use the trick of adding and subtracting L, Sn minus L plus L minus Sn. I didn't do anything. L minus L is 0. And now, this is my A, this is my B. I'm going to use the triangle inequality. Less than or equal to absolute value of Sn minus L plus absolute value of L minus Sn. This is the same thing as Sm minus L. The absolute value doesn't care about the sign. So we can just flip this. And this is less than epsilon over 2. This is also less than epsilon over 2. So this is less than epsilon over 2 by epsilon over 2. Here we are using the triangle inequality. So this is equal to epsilon. So we showed that m and m bigger than big M implies that Sm minus Sm is less than epsilon. And this is exactly what we wanted to show. So this shows that your sequence is Cauchy. This is very similar to the proof that the limit of the sum is the sum of the limits. Now, we need another lemma. Let me just state the lemma and state the theorem. I think we can maybe show, yeah. Let's finish by showing this lemma. Lemma 10.10. Cauchy sequences are bounded. Previously, we showed that convergent sequences are bounded. We are trying to say that Cauchy sequences are convergent sequences, so therefore they also have to be bounded, but we don't know that yet, so for now we have to prove this separately. But the proof is very similar to our previous results that showed that convergent sequences are bounded. So the strategy is the same, so let me just write down the formal proof. Applying the definition of Cauchy sequence, let me copy the definition here. This definition holds for any epsilon, so I can choose my epsilon. Epsilon equal to 1. We obtain that there is a natural number n such that m and n bigger than big N implies Sn minus Sm less than 1. In particular, this is true for any n and m bigger than m. So for example, we can take m equal to n plus 1, big N plus 1. This is bigger than n, so this is true. Then Sn minus Sn plus 1, this is little n, this is big N, is less than 1 for n bigger than big N. And equivalently, inequality with absolute value means this means that absolute value of Sn is less than absolute value of Sn plus 1 plus 1. Here I'm using the triangle inequality because Sn is equal to Sn minus Sn plus 1 plus Sn plus 1. Here's my A, here's my B. This is less than or equal to Sn minus Sn plus 1. Plus absolute value of Sn plus 1. Again, this is my A, this is my B, A and B. And we just said that this is less than 1, so this is less than 1. So this is strictly less than 1 plus absolute value of Sn plus 1. This is exactly what we wrote here. So this is just the proof using triangle inequality of this fact. So now let big N be equal to the maximum of this bound here note that big N is a specific number. We are saying that there exists a big N, so this specific N, big N, is the one that we are using here. Meanwhile, we are saying that this is true, not for a specific little n, but for all little n. This is true. This is true for all little n bigger than big N. This is a general n, this is a specific one. So let's take the maximum of this bound, which with all of the first elements is 1, that's 2, up until Sn. So then Sn is less than or equal to m for all n in m, natural numbers. Why for all of them? If it's small, if your little n is smaller than your big N, it's one of these, and your m is the maximum, so your m is bigger than all of those. And if it's bigger than n plus 1, then it's less than this one by what we wrote here. So this shows that this big M is a specific number that's a bound for your sequence, for your Cauchy sequence. So that's the proof. All right. Summarize what we did here. This lemma shows that convergent sequences are Cauchy sequences. Our goal, now first we showed here that Cauchy sequences are bounded. Our goal is to show that Cauchy sequences converge. And this we are going to leave for next class. So this is the opposite direction of this lemma here. And we stop here for today.